Quantifying the electromagnetic compatibility, EMC, of a circuit board presents significant challenges due to its strong dependence on environmental factors and frequency variations arising from diverse resonance structures. Achieving accurate simulation results hinges upon the completeness and precision of the models employed. Despite advancements in simulation technology, conducting a comprehensive frequency sweep using chamber-sized models remains time-consuming and prone to oversights, especially when factoring in part and process variations. Simply simulating EMC screening without designing the printed circuit board, PCB, with EMC considerations from the outset does not guarantee compliance. However, the near field, which is less influenced by distant environmental factors, offers a promising avenue for optimization. By focusing on reducing near-field emissions, PCB developers can integrate EMC key considerations throughout the design process, rather than as an afterthought. Ultimately, mastering the behavior of fields on a circuit board is essential for effectively controlling EMC and ensuring robust electromagnetic compatibility. In this scenario, the inadvertent extension of the trace beyond the reference plane, although unintended, is a common occurrence in PCB design. The resulting fields are evaluated on a plane situated 5 millimeters above the trace. Analysis of the near field reveals a notable change in field strength, suggesting a likelihood of corresponding changes in the far field. It's crucial to note that while a near field may exist without a far field, the reverse is not true. Like far fields inherently stem from near fields. The measured field strength exhibits a range of plus or minus 200 volts per meter, emphasizing the significance of addressing such unintended design aspects to mitigate potential electromagnetic interference issues. In this animated depiction, the evolving near field holds the potential to induce fluctuations in the far field, which could potentially trigger the antenna used to detect EMC noise. The near field's dynamics are visualized with limits set for the red and blue regions, ranging from plus to minus 200 volts per meter. Such variations in the near field have implications for the far field, underscoring the importance of monitoring and controlling near field behavior to ensure electromagnetic compatibility and minimize interference concerns. Extending the reference plane to establish a robust relationship with the trace along its entire length offers a significant advantage in reducing near field levels. By ensuring a strong and consistent relationship between the trace and the dominant reference plane, the fields between them can be effectively controlled. This enhancement in field management minimizes fluctuations and disturbances in the near field, contributing to improved electromagnetic compatibility and reduced risk of interference. Such measures underscore the importance of optimizing the layout and structure of the reference plane in printed circuit board design to mitigate electromagnetic effects. In the depicted animation, the reduction in the fluctuating near field serves to mitigate the potential for inducing electromagnetic compatibility EMC noise by minimizing the changing far field. By implementing measures to reduce the variability and intensity of the near field, the likelihood of generating disruptive far-field emissions that could excite antennas sensitive to EMC noise is significantly decreased. Setting strict limits, such as the specified range of plus or minus 10 volts per meter for the red or blue zones, helps establish clear thresholds for acceptable field behavior, aiding in the assessment and management of EMC risks during circuit board development and testing. In this comparison, the red line represents the electric field, E field strength, measured 5 millimeters above the trace when the reference plane is only partial. In contrast, the green line illustrates the field strength when the reference plane extends along the entire length of the trace. Notably, the magnitude of the field is substantially diminished, particularly around the 5 GHz frequency range, with the implementation of the full-length reference plane. And this reduction underscores the effectiveness of establishing a consistent and comprehensive relationship between the trace and the reference plane in minimizing E-field levels, thereby enhancing electromagnetic compatibility, EMC performance, and reducing the risk of interference or noise issues in high-speed circuitry. The comparison plot depicts the frequency content of the field for both partial plane and full plane reference configurations. Such field simulation comparisons serve as valuable tools in the development of printed circuit boards, offering insights into the effectiveness of different structural designs. The reduction in magnitude observed in the full plane reference configuration suggests a corresponding decrease in the risk of far-field failures, indicating improved electromagnetic compatibility, EMC performance. It's essential to note that while these simulations provide valuable insights, they are not intended to replace comprehensive testing procedures, but rather complement them by informing the design optimization process. Electromagnetic compatibility, EMC, has often been likened to black magic due to its perceived complexity and mystique, especially when viewed solely from a circuit perspective. However, by shifting the focus to field behavior, the intricacies of EMC can be demystified. At its core, EMC is primarily concerned with measuring and controlling electromagnetic fields. Approaching EMC from a field perspective simplifies the process, emphasizing the reduction of field magnitudes emitted from the circuit board and minimizing the impact of external fields on the design. Effective EMC management entails controlling the propagation of fields, thereby enhancing the robustness of the design. Rather than relying solely on guidelines and guesswork, a deeper understanding of field behavior is crucial in the development of printed circuit boards to ensure optimal EMC performance.